This class we discussed the program evaluation and review technique that called PERT, and we also discussed the other method that is life of balance scheduling (LOB), and we have a four learning objective shown in here. So let's talk about the program evaluation and review technique and why we need that. This one developed by the Department of Defense, the U.S. Department of Defense in 1950s, and it probability scheduling. So why probability scheduling? As you can see, everything involved uncertain. Let's see the you drive from your house to work. Now it even we have virtual, but let's see last semester when you drive uh, from your home to campus to study, to take class, etc. So you can say that someone asks you how long will it take from your house to campus. You say 30 minutes, 35 minutes, etc. But that basically the average or the most likely. It's not always the case. Sometimes there uncertainty, the traffic, stop signs, etc. So the time may be somewhere. If it's good, then we can drive for 25 minutes. But in bad condition, we can drive. It may take us 40, 45, even 50 minutes for the average time that from our house to campus 30 minutes. So with that one, as you can see, even the driving, there's some uncertainty involved, and that in the work that we do in the project, there are even more uncertain, uh, and that why we good to consider the schedule as probabilistics. So everything considered random and uncertain in the schedule, and that is the PERT program evaluation and review technique is all about. Compared to the critical path method, ADM or PDM that we just learned in the previous weeks, every activity duration is deterministic. It gives you one single numbers, how many days, how many weeks for certain tasks. But here, probabilistic. How can we do that? So before we talk about the assumption, first we assume beta distributions for the activity durations. For each single activity duration, we assume beta distribution. Of course, you learn in statistical method there are multiple distribution, but in this specific case, we assume that the activity duration follow beta distribution. And then for the project duration, we assume that is the normal distribution. So the project duration that include multiple activities. Think about that we learned in the previous lessons, CPM, critical path method. The path may include multiple activities, and in this case, the duration of project is the duration of the path, and we assume that it normally distributed. For each activity duration, assume beta distribution. For the whole project, we assume normal distribution. And the each activity duration are independent. In the real life, it may not be independent, but in this case, we assume independent activity durations. So with that one, because the probability scheduling, one activity duration may not only take one single duration, it have three, and that is we call it 3-time estimate for each activity. The first one is pessimistic time, TP, the longest time that activity may require. And that is pessimistic time. Like you drive to school, the longest time you drive, 50 minutes, then that is pessimistic time. The most likely time is the completion time having the highest probability. Just like someone asks you, how long will it take from campus, from your house to campus? You say 30 minutes. That should be a most likely time, TM. And then the optimistic time, the shortest time in which an activity can be completed. So what is the earliest time you can come here? Things like that. Or the shortest time that you take from your house to the campus is 25 minutes. So that is the optimistic time. So you can see that can apply to any activity in terms of the pessimistic time, most likely time, and optimistic time, TO. So with that one, we can be able to determine the different parameters for the activity time durations. And as we assume the activity duration follow beta distribution, so we can determine the mean or the expected time for activities as shown in this equation. So that is the TE is stand for expected time, it equal to TP pessimistic time plus 4TM most likely time plus TO optimistic time divided by 6. So that because we assume beta distribution. And because that is random, we can be able to determine the variance of the activity duration. And again, as we assume it beta distribution, then the variance is sigma squared, where sigma is standard deviation. If you recall, in statistical method, it equal to TP minus TO, which is optimistic time, divided by 6 and square. And of course, with that, the standard deviation is square root of that. And when you already determine the path of the project, including a series of activities, then we can be able to determine the standard deviation for the duration along the path that include multiple activities. In this case, you can add sigma squared. So you can add the variance, but not allowed to add the standard deviation. So that to determine standard deviation, you can add the variance of sigma square for each activity along the path to make a sum, and then use square root. So keep that in mind. Don't add the standard deviation, but add the variance as shown in this equation to determine the standard deviation of the project duration. And don't forget to square root to get the standard deviation. So how to apply that in PERT in here? First, you need to calculate the expected time, variance, and standard deviation for each activity following this equation. And then we draw the network diagram, just like we did in the CPM method, PDM or AOA. And then we apply the CPM critical path method algorithm to determine the critical path that you by now you are very familiar with and have expertise in that type of method. And then we can be able to use statistical approaches to answer multiple questions involved with the PERT. And before that, I prepare this information that you have it in here, and it's available in the reference when we review some information for when we say statistical approaches. The first one is, the normal distribution, and we have a normal table. And in statistical method class that you learn, we can be able to determine the G-score. The G-score equal to at any point X in here, and this is already standardized. So we have to standardize with the G-score, X minus X bar, which is the mean, divided by standard deviation. And then we can be able to find out the probability associated with the G-score by, first, let's see the Z. When you find from here is like 2.23. So 2.23. How can I find out probability? So G is here. The probability that you measure in this table is the area of Z to the left of Z. So you have it. The total areas here is 100%. So the probability, total probability is 100%. So from the left of the Z, if we say Z is 2.23, so on the first column, you need to find out 2.2, and the 3 is the second digits after decimal, so you find out the column with 0.03, And going down to that, so you can be able to find out that is 0.9871. What does that mean? The areas from G's in the left of Z equal to 2.23, it equal to 0.9871. It means 98.71%. So that's what we read from the table. We will apply that in the problem in today's lesson. And that explains how to read in this table if you forget what I'm talking about. Find out Z 1.8, so first column 1.80, 1.80, so you have that. If 1.81, then you go to the next column to read the number. And that is, you use the table, and that the table available on the exam 3 reference, you will use that. But in the real life, you can be able to use Excel, because in real life you can use your laptop to find out that you don't need the table. Then this slide shows you how to determine that with the normal distribution, and with any given point G score in cell A1, if you put in A1 itself, and then you can be able to use this to determine the normal distribution, the probability for the normal distribution with this function. And if you want to find out z-score given the probability, you can do that with the normal, standard normal with the inverse. So read back in there so that you can apply this in the Excel spreadsheet. So as you will see in the problem we applied for today's lessons, I just want to wrap up PERT before we apply that. So what are the benefits of limit and limitation of the PERT, program review, program evaluation and review technique? The benefit, we can say the expected project duration, so that we can be able to consider the uncertainty in the project schedule. Nothing is deterministic. And with that, the second benefit is probability of project completion before a specific date. We can be able to find that out. What is the probability, so that we know the level of confidence that we can be able to achieve the project. And similar to critical path method, we can be able to identify critical path and non-critical path, and of course the associate critical activities and non-critical activities. So those are the benefits of the program evaluation and review technique. They have limitation. The first is subjective estimate of the activity duration. We need to have 3 estimates of the activity duration: pessimistic time, most likely time, and optimistic time. That can be pessimistic, can be subjective. And we assume a beta distribution for activity duration. It may not be the case. It may follow the triangular distribution, can follow the uniform distribution. So with that, we can have trouble with other distribution that we only assume follow one single distribution, which is beta. But some research say that for activities in engineering, it tend to follow beta distribution, but not all of the activities. So that is limitation. And we assume the probability of distribution of the project completion time is the answer the probability distribution of the critical path. It may not be the case. It may follow the something we call merge bias. So 2 critical paths, if 2 different paths, one is critical, one is not critical, but there is some uncertainty. So it means that we assume the probability of the distribution of the project completion time may not be what we get in this calculation is the probability distribution of the critical path. So that is the limitation of here. So let's apply this method in problem 1, and you will see the mechanics involved when we do this method and answer different questions that critical path method ADM or PDM in the previous lesson cannot be answered.